Happy to be here on behalf of the Outer Planets Alliance to talk about the interiors of ocean worlds. I'll represent some of the work that I'm doing, but also try to form a bridge to exoplanets, including some work that Rory and I have been talking about and developing. So the points that I want to make to you are that potentially habitable ocean worlds, there are many of them in the solar system. I'm depicting my best representation of possible interiors for the most prominent ones, for which we have the best evidence for interior oceans. And they represent an abundant analog, or an analog to an abundant class of possible exoplanet. So these deep oceans, they expand the parameter space of ocean properties that we need to consider beyond what we usually think about for Earth. And there's obviously an analog to super Earth with deep ocean. I'm mostly interested in the ones that are covered in ice because that's the most direct analog. And those material properties are becoming available through work that a group that I'm working with and others are doing. And so the main, if there's one point that you take away from this, I hope that it will be that high pressure ices are not always a barrier to water rock chemistry. That's an insight that's come both from the lab work that I mentioned and also to some numerical work, a lot of it that Christoph is involved in. Unfortunately, he had to leave, but he knows all this stuff. So I like to share this. I haven't seen this slide in this forum yet. This is from a paper actually describing the JUICE mission to Ganymede by Olivier Grasset, and it's making the point that the JUICE mission is meant to help us understand deep habitats in the outer solar system. That is building on this idea that in addition to the conventional habitable zone depicted here, beyond the snow line, are many more possible habitable regions, and this graphic helpfully depicts how the snow line and the habitable zone will vary for different systems, different stars. So thinking about these deep habitats, there are a lot of questions that apply to ocean worlds, both in our solar system and beyond. So I just took a quick moment to write down some of the things that I've been thinking about. And they group into sort of three categories. There's solid ice geophysics, both ice one, the lithosphere. We have a chance to study solid state convection in another material, not rock that we study on Earth, but instead in ice. And understanding the transport of the ice is intrinsically related to understanding the redox transport, that is how materials move in and out of the ice. We also have the chance to study exo-oceanography. There are groups in the last 10 years who have been studying how tidal properties, whether tidal heating can happen in oceans, how convection works in really deep oceans. And lastly, there's this question of integrating everything to ask, what is the redox evolution of an ocean world? And what is the resulting ocean salinity, pH, chemical affinity for metabolism? These are things people are now beginning to talk about based on measurements at Enceladus, but they're also things that we can speculate about based on what we currently know in terms of geophysics and geology at Europa. So I'll talk about that a little bit. I thought I would give some perspective on the trajectory of knowledge of ocean world just by focusing on the Jupiter system for a little bit. So here's what we knew at first about the large satellites of Jupiter. This is what Galileo drew in his notebook 410 years ago. And this is what we know after the Galileo mission about those moons. So 3 of them are ice covered, 1 of them is not because it's very volcanically active, very strongly tidally heated. We should know much more after Europa Clipper visits Europa and incidentally the other moons, but we're focused on Europa. And after the JUICE mission visits Ganymede, I love that the solar panels are shaped like the Swiss flag. So that's really exciting that we have these missions that are going to tell us a lot about these objects, including a lot of geophysical measurements that can tell us about how these bodies work as a whole, and again, how that affects the redox transport and chemistry in these objects. So just some big picture stuff then about these objects in terms of Earth-ocean masses. In the solar system, we have a representation of objects that have global oceans that have less than an Earth ocean mass, possibly up to 2 ocean masses in the case of Europa, and as many as 25 ocean masses. I should point out in the case of Ganymede that much of that will be frozen. Nevertheless, this is a lot of water. It constitutes a geophysically significant part of the body. And so we have to think of this in geophysical terms. So zooming into Europa then, this is a nice schematic that summarizes a whole talk's worth of information about Europa. But in broad strokes, oxidants are formed at the surface through radiation at the surface. Europa's ice is very active. The surface is geologically young, so we think those oxidants make their way into the interior. We think because Europa is heated tidally, it's possible that high temperature hydrothermal systems exist. This was a focus of research for quite a while, but there's also the possibility that low temperature hydrothermal systems exist instead. In fact, those would be more abundant if there were less tidal heating in the interior, because the depth of percolation of fluids would facilitate the more extensive water-rock interaction. And so part of my work is thinking about how that works. So here's, as a function of tidal heating in Europa's seafloor, the estimated redox flux of both of oxidants. Here's Earth's net O2, here's Earth's net H2, just for a metric. Those are based on Earth system science studies. And then here's the range of oxidant fluxes for Europa's ocean based on what literature is out there. And some of that literature has looked at the abundance of H2 from high temperature hydrothermal activity. So if you think about the offset between hydrogen and oxygen in Europa, you can see that for certain assumptions about the O2 flux, the offset is very similar. And this is a total numerical basis, that is moles per year. But if you think about it in a per unit area basis, the numbers are actually quite large, comparable to Earth's. And bringing serpentinization into that, this is some of the work that I've done. As you decrease the amount of tidal heating, again, the depth of the fluid percolation increases, and the rate of fluid percolation into the interior as Europa cools is also higher. So the corresponding flux of hydrogen is higher. So that's an interesting story, and it's something that we will be able to refine thanks to Europa Clipper. So going to the larger objects, Ganymede and Callisto being the two large objects at Jupiter, but Titan also being in that class of objects, we can ask about where high pressure ice exists, which forms of high pressure ice, whether solid state convection occurs in those ices, and importantly for astrobiology, does the high pressure ice prevent water rock interaction? So I'll get to that, but first I want to make the connection to exoplanets. So what about habitable ice covered exoplanets, or HICEPs? Could they exist? What's the prevalence of them? So this is a nice figure that Rory put together based on certain assumptions about the possible super Europas. Namely, these are super Europas that would be Earth mass and that have certain tidal parameters. So we expect that there could be, as a function of the size of the star, there could be quite a few of them, somewhat close into their planet. In fact, if we look at the Kepler Catalog, it's possible that there are quite a few that have already been observed. So I'm hopeful that in the next decade or so, we'll understand more about habitable ice-covered exoplanets. It's possible that we already know of one, namely TRAPPIST-1H, which appears to be is plausibly a water-rich object based on some work that was published by Cayman Winterborn. Okay, so bringing all this back then to similar thinking about bodies in our solar system, there's this nice figure from Huisman et al. Putting together the classifications of these different objects. I just want to relate this. So we think about mass-radius relationships in exoplanets. There's a similar way of thinking of things in terms of density versus size. And it's notable that the very large objects are very low density. It's interesting that Europa is in a class more analogous to the Moon and Io, possibly because of the tidal heating that's occurred there. So that's maybe a useful way of thinking about what might be happening there. Now, what is the deep interior of these large objects like? How can they be so low density? So this is a topic people have been thinking about and recently have made a little bit of progress on. So one of the things that we have the luxury of having in our solar system is spacecraft measurements of the gravitational moment of inertia. That is, that's a measure of how concentrated the mass is toward the center. And so here you can see the moment of inertia as measured by the Cassini mission for Titan. That is the large solid circle there for Titan. And for Ganymede, the large solid circle in blue there. and their masses are known. The error bars on the mass and moment of inertia are about the size of the circle that's shown there. So what's also shown is interior structure models for objects of the size of Titan and Ganymede, assuming entirely carbonaceous chondrite composition, that's the dashed line, but then adding certain amounts of volatile material in the interior structure models that were used in this recent paper by Neri. The point being that it's easier to get a reasonable interior structure if you add organics. I think this is really important at Titan. I'll show some of my work on this later, because you can't explain Titan's low density without adding a lot of organics to the interior. I guess I can just point out what this NH means. So in Titan, we don't know if the interior is actually hydrostatic, which is an assumption that's made when you model these objects as spheres of concentric spheres of increasing density toward the interior. So if you account for the possible non-hydrostaticity of Titan, you come up with a lower moment of inertia. And that's actually the value that I'll use in the stuff that I'll show a little later. But just finishing the thought about this paper by Neri, there's this nice summary of the interior structure models for Titan and Ganymede. Here, darker blue is a high pressure ice layer, and lighter blue is a salty ocean. It turns out that the tidal love number constraints from Titan imply a very salty ocean. It's not clear how salty the ocean should be for Ganymede, but the green here pictured for Titan is the organic rich material. So this is somewhat at odds with the idea that pressures are so high, up to a GPa at the seafloor for Titan. Pressures are so high that they would prevent significant fracturing, because that assumption would tell you that water-rock interaction is difficult. But here it seems that in order to understand Titan's interior, we require water-rock interaction to have occurred. So that's a tension that hasn't really been resolved. One possibility is that Titan formed from a lot of organic rich materials that then exhaled from the interior. But that's again a geophysical question that we're continuing to think about, and which bears on the formation of larger super watery exoplanets. So analogous to this, well, I guess I should take the opportunity to point out Ganymede's a different world. We have good evidence that there's an iron core, in fact, a molten iron core, because Ganymede generates its own magnetic field. So Ganymede's really a planetary body in its own right, which hopefully will teach us a lot about potential exoplanet analogs. Another aspect that people have been thinking about for Ganymede, where the high pressure ices are very thick, is what is the dynamics in the high pressure ice layer? And so recent numerical studies accounting for the formation of fluids in the high pressure ices, starting from the insight that the top of the high pressure ice layer is at the melting point. So you have a hot thermal boundary condition when you're considering what is the temperature profile in the interiors of these objects. The accounting for the formation of fluids, it's been realized that you should form a temperate layer near the top of the high pressure ice, namely a layer that has fluids that form in pores. Those fluids are water, and we have to flip our intuition about ice, because for high pressure ices, those fluids are going to be less dense than the solid. So what you could think of is sort of hydrothermal systems in high pressure ice, right? These are fluids that want to migrate upward, and so you should have some kind of circulation, some kind, in the ice. In addition, I should point out what the temperature profile here is the solid curve is the melting temperature, or the dash curve rather, and the red is the profile of the maximum temperature in this particular model, and the blue is the lowest temperature. So you can see there's quite a range that can be experienced, and that's due to the presence of fluids. The other insight here is that at the lower boundary, which is a kilometer or more thick, you should also form pockets of fluid. And so there's a question of what is the extent of water-rock interaction where those fluids are forming. And another question that I'll get to is, what if those fluids are salty? So again, just want to hammer home this point that high pressure ice is not a complete barrier to water-rock interaction. Rather, it's an interface, and one that delays the movement of fluids from the rock interface to the ocean. You can think of that as a redox gradient, in fact. So I think that's also of interest for astrobiology. It makes the chemistry of these worlds even more interesting and complex. So looking at the chemistry of these worlds and now getting some of the experimental work that I mentioned, I'm showing here some work by Baptiste Journeau, currently a postdoc working with us at the University of Washington. During his PhD work, he created precipitates of ice 6 and 7 in a diamond anvil cell in the presence of sodium chloride. And he showed that as you increase the abundance of sodium chloride in your sample, you go through a transition where the density of the fluid becomes higher than the density of the ice. And so he could turn the diamond anvil cell over and watch the ice float upward. And so you can imagine as these oceans freeze out and become saltier, as the salt is precipitated into the ocean, or rather fractionated into the ocean, you could start to undergo some kind of inversion where the ice has become unstable. And so that's a weird dynamical thing, again, that challenges our intuition for how these worlds work. So to think about these kinds of problems, we've been doing a lot of extensive laboratory work, both in fluids and solids. So here's just a smorgasbord of things that we've done. In the upper left, I'm showing sound speeds for water, a very dense data set collected by another postdoc, Olivier Belanger. And those sound speeds are actually a second derivative in both pressure and temperature of Gibbs energy. So this is some chemistry. I won't show you much more chemistry beyond this. I will show you some geophysics though. So the idea though is that if we know the sound speed, we are obtaining a surface in pressure and temperature that can be integrated to give us the Gibbs energy. So we have a sensitive measure of the Gibbs energy, which is a unifying property that gives us all the other properties that we can use for our geophysical investigations. So thermal expansivity, density, heat capacity, bulk modulus, that's actually a parameter in tidal dissipation. In addition to that, Baptiste he's just published a paper about the sea freeze model. It's a numerical framework for capturing a lot of experimental work that he's done. He's actually refined the phase boundaries for different ices. So just pointing out so that there are a lot of different ices. I mentioned ice 6, there's also ice 5, a slightly lower density, lower pressure phase. Ice 3, ice 2, a very low temperature, lower pressure phase. So he's mapped out these interfaces in Gibbs energy space. So he's actually corrected some measurements from Bridgman from more than 100 years ago. So we're improving the fundamental chemistry of water in preparation for being able to model these worlds in much more detail. So my role in that is to use the data that we're getting and to incorporate it into radial structure models for these worlds. So returning to this schematic for these larger worlds, I can treat the thermal profile of the ice 1 layer. In the conductive case, in fact, there's an analytical representation for that, but I also can treat solid state convection using available parameterizations. It's important to point out that in an ocean that's hundreds of kilometers thick, the Rayleigh number is very high. Rayleigh number depends on the cube of the thickness, and these worlds have some amount of radiogenic heating from the interior. So Rayleigh numbers are going to be on the order of 10 to the 20th. Anything higher than 10 to the 3rd is sufficient for convection. So these are strongly convecting worlds. And so we can treat the adiabat, notably the adiabat depends on those thermodynamic properties I just showed you, thermal expansivity, heat capacity, and density. So I can use available information, and I bundled it into this software I called Planet Profile. I can use thermodynamic information to explore how salinity and different assumptions about the ice affect the interior structure using available properties of the different worlds. As summarized in this paper we published a couple of years ago. And so we can do things like predict the density structure for different oceans as a function of pressure, and look at the same data to look at how the adiabat differs for different assumptions about the ocean temperature. So here just highlighting for Europa, for the range of ice thicknesses for Europa, how the ocean adiabat cools if you assume seawater as the composition. The seawater equation of state that's available for Earth's ocean is sufficient basically for Europa. It becomes numerically unstable for higher compositions if you assume the ocean is twice the salinity of Earth's ocean. We can also look at the electrical conductivity, which is a parameter if you're doing magnetic induction studies, which JUICE and Europa Clipper will do at Ganymede. So I need to wrap up here. I'm just going to show you a couple more things. So at Titan, we can again look at the effect of sodium chloride versus magnesium sulfate. This is using a sodium chloride equation of state that we're about to publish. And I just want to point out that the adiabat that I mentioned earlier has a different slope for sodium chloride than for magnesium sulfate. It's is not as slopey for magnesium sulfate. So interestingly, the temperature at the bottom of this sodium chloride rich ocean is warmer. Well, actually, what it means is that you have less high pressure ice in that case. I've also chosen different ice thicknesses for Titan, so that kind of makes the interpretation a little more complex. We can predict the love numbers, the tidal love numbers, K2 here, the tidal potential love number, as a function of ocean density. And in the model so far, we've been unable to meet the high value of 0.6 inferred by Cassini. So we need to look at even higher salinities. Last thing I'll mention is we have work that's ongoing by a postdoc working with me at JPL, looking at the volatile escape during Titan's formation, so bringing things back to the formation models. So this is using the similar thermodynamics now for minerals, using the Perplex framework. And here, just showing along geotherms for Titan, in fact, the ones that I just showed you, the escape of fluids as a function of mass percent along those temperature profiles. You can imagine integrating from 0 up to the temperature of that geotherm, and then breaking that data down in terms of oxygen-rich materials, mainly water, and carbon-rich materials, mainly CO2. So I'll skip magnetic field measurements. Ask me after my talk, and just leave my conclusions there. So thank you very much.